Imagine showing a neural network a photograph and asking just this: is there anything interesting here at all? Not what it is yet. Not where it is, just, does something worth noticing exist in this image? To answer that question, the model doesn't need much. One output is enough. If the value is high, the model is confident that something is present, and if the value is low, the model believes the image contains nothing relevant. This number isn't a strict yes or no. It's a confidence, a smooth signal that tells us how sure the model is. But that alone isn't very helpful. If something is present, we don't want the model to simply announce it. We want it to point. That means drawing a box. To describe a box, the model must specify two things. First, where the box begins, a reference point inside the image, given by two coordinates. Second, how large the box is, its width and its height. Once these four numbers are known, the box is fully determined. At this point, the model can say, something exists, and it lives exactly here. But we're still missing an important piece. We don't want anonymous boxes. We want meaning. So the model also predicts a set of scores describing what kind of thing is inside the box. In the original YOLO setup, there are several predefined categories. Each category gets its own score, and the largest one tells us what the model believes it has found. Now, pause for a moment. And count what the model is producing. 1 number for existence. 4 numbers for position and size. And a collection of numbers describing the object's identity. Altogether, this forms a compact description of a single detected object. At this stage, two problems immediately appear. First, how do we train one network to learn all of these predictions at the same time? And second, what happens when there isn't just one object in the image? A first attempt might be to simply ask the model to predict multiple boxes at once. Give it extra outputs, let it describe two things instead of one. But something subtle goes wrong. Those boxes still share the same identity prediction. So even if the locations are correct, the model is forced to treat different objects as if they were the same kind of thing. This is where YOLO changes perspective. Instead of treating the image as a single canvas, it divides the image into a fixed grid of regions. Each region is now responsible for whatever appears inside its own boundaries. Inside every region, the model predicts a small number of possible boxes. Each box carries its own confidence and geometry, while the region itself predicts what category it believes it is observing. By doing this across all regions, the model can describe many objects at once spread across different parts of the image all in a single pass. This structure leads to a large but very organized output, a grid of regions, each producing a consistent set of predictions. To avoid chaos, one rule is enforced. If an object overlaps multiple regions, only one region is allowed to claim it, the region that contains the object's center. All other regions ignore it. This prevents the same object from being detected multiple times. With the structure defined, training can begin. During training, the model compares its predictions against the true answers. But here's the challenge: most regions contain nothing at all. For empty regions, there is no correct box to compare against. So YOLO introduces a simple gate. When a region truly contains an object, the gate is open and errors are counted. When it doesn't, the gate is closed, and location errors are ignored. This way, the model isn't punished for guessing boxes where nothing exists. A similar idea applies to box size, but with an important twist. Instead of comparing sizes directly, the model compares their square roots. Why does this matter? Because a small mistake on a tiny object is far more damaging than the same mistake on a large one. The square root transformation naturally increases the penalty for errors on small objects, helping the model learn precise localization where it matters most. Next comes confidence learning. Regions that truly contain objects are trained to produce high confidence, while empty regions are trained to produce low confidence. But since empty regions are far more common, their influence is deliberately reduced. Otherwise, the model would learn to always predict nothing just to be safe. Finally, the The category predictions are trained, but only in regions where an object actually exists. There's no reason to classify emptiness. One final weighting increases the importance of getting box geometry right, ensuring the model focuses on precise placement. And with that, the full idea comes together. A single neural network. One forward computation. Simultaneous predictions of existence, location, and identity, all at once. The model doesn't scan. It doesn't revisit the image. It looks once, and decides everything in one shot. That is the idea behind You Only Look Once.